So, good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems, IISc. Today's talk is by Professor Salil Kashyap, and he will be speaking on the feasibility of wireless energy transfer using intelligent reflecting surface in next generation IoT networks. Professor Salil Kashyap is an assistant professor in Department of Electronics and Electrical Engineering at IIT Guwahati. Before joining IIT Guwahati, he was a senior DSP engineer at Marvell, where he designed physical layer algorithms for the next generation WLANs. Prior to that, he was a postdoctoral researcher at Linköping University, Sweden. He received his PhD from IISc Bangalore, MTech from IIT Guwahati, and BTech from NERIST. His research spans areas of wireless communications, networks, and signal processing with emphasis on mathematical modeling, performance analysis, and algorithm design for 5G and beyond 5G cellular communication systems. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Over to you, Professor Kashyap.
Yeah, thank you. Thank you for the kind introduction. Yeah, so I'll go full screen now. To the participants, please feel free to interrupt in case you have any questions. Yeah, so yeah, I hope this is full screen now. Can somebody confirm?
Yes, sir.
Yeah, thank you. Yeah, so I'm going to talk about the feasibility of wireless energy transfer using intelligent reflecting surface in next generation IoT networks. And this is a joint work with my students, Chandan Kumar, Supreet Sharma, and a colleague, Dr. Sarvendranath Rimalpudi. He's a colleague here in the Department of EEE at IIT Guwahati. All right. Yeah, so basically it is predicted that a large number of IoT devices will form a core component of next generation wireless systems. Yeah, just to give you a feel for the numbers, the number of IoT devices, they are expected to grow at an unprecedented rate to around 30.9 billion globally by 2025, given the current estimates of around 13.8 billion. Yeah, and we all know the reason for such an explosive growth in the number of IoT devices has primarily to do with the various applications that they support. Ranging from manufacturing to healthcare to self-driving cars, wearables, intrusion detection. All right. So therefore, there is a need to provide cost-effective solutions so that these sensor nodes are able to communicate reliably over the air. And then most of these sensor nodes, they run on limited capacity batteries. So there is a need to provide them with perpetual energy supply. Now, essentially, there is a need to replace or recharge their batteries. Now, sometimes these sensor nodes may be located or may be placed at hazardous or inaccessible locations. Then a key question that we are interested in is, can they be charged wirelessly? Wireless energy transfer is one promising energy harvesting technology where the sensor node harvests energy from electromagnetic signals. All right, and this can be one potential solution to power these IoT devices without wire. Yeah, it helps you get rid of the hassle of battery replacement, and it thus increases the battery lifetime of energy-constrained IoT sensor nodes. However, one must understand that there are several challenges that need to be addressed in order to implement WET efficiently. The first challenge that must be addressed is that only a very small fraction of the energy which is radiated by a source can actually be harvested. Yeah, this has to do with the severe path loss that the signal undergoes as it propagates from the source to the destination node. And then there are limitations associated with the energy harvesting circuitry as well at the sensor node. Yeah, and this limits the range over which energy can be transferred wirelessly. The second thing that the second challenge that we should understand is that the receive power levels that are suitable for information decoding in conventional wireless communication may not be appropriate for turning on the harvester in these sensor nodes. Yeah. So the role that receive SNR plays in information decoding, absolute receive power plays that role in wireless energy transfer. So essentially, it is the absolute receive power that is of interest, unlike the receive SNR in conventional wireless information transfer networks. The design must also ensure that these sensors harvest more than what they consume in tasks related to channel estimation, sensing, computation, and communication. Now, I'll just give a sample of some of the initial attempts that we made with regards to wireless energy transfer. So one can essentially use massive number of antennas at the source to boost the performance of energy transfer. Yeah, so one can exploit essentially the huge array gain offered by these massive number of antennas, yeah, to boost the strength of the receive power. However, the problem with this solution is that while these antenna elements themselves are cheap, the radio that drives these antennas is bulky, costly, and power hungry. Yeah, so each antenna requires a radio frequency chain. If we are talking about the transmit RF chain, then every transmit RF chain consists of a power amplifier, a digital to analog converter, and up converter. Yeah, and they consume power at the same time. They make the hardware complex. Very recently, in 2021, Xiaomi has come up with a prototype for wireless charging. Yeah, they've named it Mi Air Charge. Now, this essentially is a wireless charging solution that can provide a 5-watt charge to multiple devices located within a few meters. Yeah, the transmitter for this prototype, it consists of an array of 144 antennas that essentially transmit millimeter wave wide beams to charge devices. So essentially, as you so you can imagine this scenario of walking into a room and your mobile starts getting charged automatically, yeah, wirelessly. Yeah, so the thing with this Mi Air Charge is that the transmitter is bulky. Yeah, it essentially is of the same size as a table right next to your couch in the living room. All right, so it uses 144 antennas, so you can understand the number of RF chains that have been deployed, and that makes it costly and a power hungry solution. This is yet to hit the consumer market, but then the point that I wish to emphasize here was there are solutions out in the market that use an array of antennas to beamform energy towards devices. Now, why just mobile phone? Your desk, your lamps, headsets, all that can be charged wirelessly within a range of few meters if such a product comes out in the market. But then the problem with these is that they deploy a lot of radio frequency chains that consume power and make the hardware complicated. Yeah. Now, in order to tackle that problem, one possible solution could be to use an intelligent reflecting surface. Now, intelligent reflecting surface, again, it's a promising 6G technology. It's a buzzword these days. It essentially consists of a metamaterial surface comprising of an array of low-cost reflecting elements shown here in green. Now, each of these elements, it is capable of inducing an amplitude and a phase change on the signal that's incident on it. All right, and if the phases of each of these elements can be programmed appropriately, then one can essentially ensure that the various copies of the signal that reach the user via the direct path or via the reflections through the IRS, they add up in phase at the user. Okay, so one can essentially boost the strength of the receive power through constructive interference, yeah, through coherent addition of different copies of the same signal. Now, the advantage with these intelligent reflecting surfaces is that these elements, they do not require dedicated RF chains. Okay, they are easy to deploy. They can be easily mounted on the walls of a building. All right, and if the phases can be configured in such a way that coherent addition of different copies of the signal can be achieved, then it can help you achieve higher data rates, improved coverage, and efficient wireless charging of IoT devices. Yeah. Now, one typical architecture of IRS essentially consists of 3 layers. The outer layer is basically the tunable metallic patches printed on a dielectric substrate, that directly control the direction in which the reflected signal goes out. Then there is a middle layer or the intermediate layer where the copper plate essentially helps you minimize energy leakage during IRS reflection. And then there is this third layer, the inner layer, where you have the control circuit board comprising of pin diodes to control the phases that these elements can induce. One can also control amplitude by changing the resistance or the impedance associated with each of these elements. And then there's an FPGA-based controller which can help you configure, which can help the access point basically set the amplitude and phases of these IRS elements. Now, jumping straight into the system model that we'll focus on during the talk today. So we'll look at a network where the source is equipped with multiple antennas and just a single RF chain. Now, the motivation behind using a single RF chain is that it reduces cost, power consumption, and hardware complexity. We'll look at a generic case where the source may be equipped with fewer RF chains than the number of antennas, not necessarily one, a little later in the talk. But for now, the source is equipped with just a single RF chain and M antennas. We model, or we consider that the channel between the source to the user is relay faded. All right. The channel from the source to the IRS or from the IRS to the user is Gaussian faded, meaning these two channel components comprise of both the line of sight and the non-line of sight components. We assume TDD mode of communication, and some of the initial indoor and outdoor field trials have confirmed that this TDD mode holds even in, the channel reciprocity basically holds even in channels via the IRS. Now, what do I mean by channel reciprocity? Generally, when these channel coefficients have to be estimated in practice. Now, in order to estimate the channel coefficients, users send out pilots on the uplink. And based on what the source observes, it can estimate the channel between the source and the user, both along the direct path and the reflected paths. But then only if the channel is reciprocal, the estimates obtained on the uplink can be used as a proxy for the channel on the downlink. All right. Now, why is channel estimation required here in this model? So basically, we see that there is just a single RF chain. So the source must dynamically connect the RF chain to one among the M antennas based on the instantaneous CSI. And not just that, the source must also configure the phases at these IRS elements to achieve coherent addition of signals, the various signal copies that reach the user. All right, so we assume that the mode of communication follows the TDD protocol, and and the key questions that we are interested in is, so we understand that there is just a single RF chain, M antennas. So we want to come up with an antenna selection rule that incurs as low overhead as possible in estimating the channel. And at the same time, using the index of the best antenna selected, how do we configure phases at the IRS? What would be the impact of channel estimation error on performance? Now, when we talk about performance, we'll look at the metric referred to as the probability of outage in energy transfer. Now, how do we declare outage in such an energy transfer scenario? So an outage is declared whenever the sensor node ends up consuming more than what it harvests. All right, so we'll look at the impact of estimation error on performance. We'll look at the impact of discrete phase shifts. Now, what do I mean by discrete phase shifts? These IRS elements, although for the most of the discussion during the talk will focus on continuous phase shifts, meaning these IRS elements can induce are equipped with infinite precision elements. But then in practice, one possible architecture uses pin diodes in order to induce phase shifts. So for example, by controlling the biasing voltage of the pin diodes attached to each of these black elements here, one can induce phase shift of 0 and pi. Yeah, so essentially one pin diode can induce 2 levels of phase shift. Similarly, 2 pin diodes can induce 4 levels of phase shift. Yeah, so but the thing that we must understand is that for IRS, I mean, any practical IRS that will be built can only induce a certain certain specific quantization, I mean, certain specific phase shift levels. Yeah, so because these elements are sub-wavelength sized, and therefore not many pin diodes can be fabricated on each element. So it is equally important to look at the impact of discrete phase shift on performance. We'll then look at extensions to subset antenna selection. So essentially the case where the source does not necessarily have a single RF chain, may have few more RF chains, less than the number of antennas. We'll look at extensions to multi-user scenarios. So initially we'll just focus on wireless energy transfer using IRS to a single user, and then we'll look at how to extend that analysis to a multi-user scenario. And the key question that we will be interested in is, can we trade off active RF chains at the source with passive elements at these IRSs while keeping the receive power level at the user at the same level? Yeah, so that a reasonable rectenna efficiency can be maintained. Yeah, so all right, so these are the key questions we'll be interested in it. Now let us dive deeper into the model and try to understand what we have done. So we'll follow this ad hoc antenna selection rule, where among the M antennas, the best antenna is the one that sees the strongest channel to the user along the direct path. All right, so that's what we have written here, HSUK, and you take a max over these M different antennas. Yeah, now, yeah, so we'll discuss other possible options here, but for now, this is the antenna selection rule. Now, once we have found the index of the best antenna at the source, the signal received at the user will essentially equal HSUA. So this denotes the channel between the source and the user. This denotes the channel from the the best antenna at the source, to the user. Plus, this essentially denotes the path via the IRS. So essentially this capital HSI is an M cross N channel matrix. But then when the best antenna is selected, HSI essentially denotes the 8th row of this matrix HSI. Yeah, so there's a 1 cross N row vector multiplied with a diagonal matrix of dimension N cross N. So theta models the phase shift induced by each of these N IRS elements. And then we have HIU that models the channel between the N IRS elements and the user. Yeah, so there's essentially an N cross 1 column vector. Yeah, so this is the effective channel multiplied with the symbol XS that is sent out from the best antenna, which is A in this case, plus the noise. Yeah, now the contribution from noise will essentially be negligibly small. So one can, based on YU, one can write down the energy harvested by the sensor node. Yeah, and that would essentially equal. So all we have done is there's a complex Gaussian channel coefficient. We have written it in amplitude and phase form. Yeah, so rho SU denotes the Rayleigh fading part. Yeah, and plus the channel via the IRS. So rho SIUAN. So this is the channel from the 8th antenna at the source to the user via the nth element at the IRS. This is the effective phase. So the phase induced along the path from the source to the IRS added to the phase induced along the channel from the IRS to the user. Yeah, so that's the effective phase along induced. FIN is the phase induced by the nth IRS element. All right, and this constant gamma, it is essentially a function of the transmit power. Tau C denotes the coherence interval, essentially the duration over which wireless energy transfer takes place. And eta R denotes the rectenna conversion efficiency. All right. So each of these sensor nodes, they are equipped, they have energy harvesting capability, and they are connected to a rectifier. Yeah. So what is the conversion efficiency of that rectifier? Now, to maximize harvested energy, now this is straightforward. In order to maximize energy, harvested energy at the user, the nth element at the IRS would be configured in such a way that the reflected copy adds up in phase with the copy via the direct path. Yeah, and this will ensure that. Now, with this phase setting, the energy harvested at the user will essentially be the contribution from the direct path plus the contribution via the reflected path. Now, I've tried to keep as little math as possible, but then, yeah, so just to give you key idea about straightforward, but outage analysis under perfect CSI. What are we interested in? We are interested in computing the probability that energy harvested by the user is below a certain threshold ETH. All right, now ETH will in general be a function of the amount of energy that the sensor node spends in sending out pilots or in performing other processing tasks. Yeah, so this is the energy harvested that we obtained based on the model. And we are interested in computing the probability that this goes below ETH. Now, if you notice, rho SUA is essentially the max of MIID Rayleigh random variables. Yeah. Y is the sum of product of Rayleigh fading channel coefficients. Yeah, they are independent. And the terms, the terms are also independent of each other. Now, given these two, one can express the probability of outage. Yeah, so sorry for the typo. PO essentially means the same as P outage. So one can express outage probability in terms of the probability density function of these two random variables. Now, one can invoke central limit theorem to essentially model Y as a Gaussian distributed random variable, and then one can write down the PDF of Y. All right. Now, so this was, there's a performance that one can get with perfect CSI. But then in practice, the channel coefficients will have to be estimated to perform antenna selection at the source and to configure phases at these IRS elements. Now, let us look at one possible way to estimate the channel. Yeah, so there's a two-step procedure. In step one, the IRS is turned off. And since there is just single RF chain, so even during the channel estimation phase, only one of the antennas can be connected to the RF chain. Therefore, user needs to send out M pilots in succession in order to estimate the M channel coefficients, yeah, from the M antennas to the user. Yeah. So based on what the source observes, it estimates the direct path CSI. And once it has the knowledge of these M channel coefficients, it can select the best antenna A. In step two, source switches the RF chain to the best antenna, yeah, A, and IRS is turned on, yeah, one by one. User sends out N pilots in succession. Now, what the source estimates is the sum of the direct path and the reflected path CSI corresponding to the best antenna selected. Source would subtract the direct path CSI to obtain the reflected path CSI. Yeah. Now, the key advantage with this simple antenna selection rule is that it only requires M plus N pilot transmissions in order to select the best antenna A at the source and to configure the phases at these IRS elements. Yeah, I'll discuss the other optimal selection rules which have been discussed in the literature, and we'll see how this rule is near optimal while requiring fewer pilot transmissions. But then once we have the channel estimates of both the direct and the reflected path CSI, so one can write down the linear MMSE estimate of the direct and the cascaded channel coefficients. And the joint AS and the passive beamforming rule modifies. Yeah, so one can find the index of the best antenna now based on the channel estimates and configure phases at the IRS based on the estimate of the phases. Right. So Now, the key step, one of the key steps involved in outage analysis with imperfect CSI is that, so what we end up estimating is not these individual links. What we end up estimating is the product of the two channel coefficients. Now, in order to make the analysis tractable, we model this cascaded channel as a Rician random variable. Yeah. Now, so on the right hand side, what we have done is we have plotted the CDF of the estimate of the cascaded channel. All right. And what we observe is that the Rician model is a good fit for the estimate for the of the cascaded channel for larger to moderate Rician factors. For small Rician factor, the Rician model is not perfect. However, it tracks the empirical CDF of the cascaded channel coefficient reasonably well. All right. So, yeah, so the outage analysis under imperfect CSI, we do an approximate analysis where we model the cascaded channel as a Rician random variable, and we see that the fit is reasonably tight. Now, coming to the benefits of the proposed antenna selection rule. So the antenna selection rule that we just discussed, it is only based on the direct path. I mean, we just worried about.
Can I interrupt?
Yes, yes.
Yeah. In the previous slide, Nilesh here,
Yes.
just a question. If it were perfect CSI, the cascaded channel is Rician in your model. Is that correct?
Yes, sir. Cascaded channel is Rician. Yes.
So you're basically saying now with imperfect CSI as well, you'll model it as Rician, but with different parameters.
Yes. Yes.
And how do you get those parameters?
So we do an LMMSE estimate of the direct and the cascaded channel.
Okay. No, in the sense you say you model the cascaded channel as a Rician RV. So yes, the shape and scale parameters for that Rician RV, how do you get?
Sir, we only need the mean and the variance.
Yeah, mean and variance.
Yeah,
how do you get it with cascaded? For the imperfect CSI, how do you get the?
With estimated CSI.
Ha.
Yeah, so based on the observables, one can write down the linear MMSE estimate of the cascaded channel coefficients as well.
All right.
Yeah.
Okay, then you basically calculate it out.
Yes.
That. Okay, cool. Thanks.
Yeah, so our antenna selection rule only accounts for the channel along the direct path. But then there are optimal antenna selection rules, which essentially consider both the direct and the reflected path CSI in order to figure out the best antenna index. There's a simpler version of the rule as well, a low complexity version of the rule as well, which selects the antenna based on mod HSU M hat plus the sum of the cascaded channels. Yeah, and the authors here have shown that the optimal antenna selection rule requires M plus M times N pilot transmissions. So where M denotes the number of antennas at the source and N denotes the number of IRS elements. While this low complexity antenna selection rule requires 2M plus N pilot transmissions. I mean, why it requires these numbers? The details are here in the paper. If you're interested, I can take it up again towards the end of the talk. But the key idea that we wish to highlight here is that the proposed antenna selection rule that works only based on the strength of the direct channel is near optimal while requiring fewer pilot transmissions. It only requires M plus N pilot transmissions. Now we do observe a degradation in performance with this OAS and LAS rules, because by design, they have been designed to maximize receive power under perfect CSI. But then, since they require a larger time interval for estimating the channel coefficients, relatively lower time, a relatively lower fraction of the coherence interval is available for wireless energy transfer with these two rules. All right, so this is the reason why, as the number of IRS elements increase, the outage probability degrades with these two selection rules compared to the proposed AS rule. Yeah, while with smaller number of IRS elements, we see that the proposed ES rule gives very close performance to these two rules. And this possibly has to do with the fact that these two hops induce path loss, which is like magnitudes higher than the direct path. So effectively, the direct channel is strong enough, and antenna selection is fairly robust as far as the rules are concerned. So a few more examples. So here what we do is we plot probability of outage in energy transfer as a function of the source transmit power. We do that for both perfect and estimated CSI and for different configurations. So C equals 1,1 essentially means source with single RF chain, single antenna. C equals 1,4 means refers to a source with single RF chain, 4 antennas. Yeah, these two set of curves are with 100 IRS elements, and then these two set of curves are with 200 IRS elements. So one can notice that so while keeping the outage probability fixed at 10 power minus 4, C equal to 1,4 gives you about saves you about 5 dV watt power just by adding 100 IRS elements. So C equals to 1,4 with 200 IRS elements saves 5 dB watt power compared to C equals 1,4 with 100 IRS elements. Yeah, so one can obtain substantial savings of transmit power by increasing IRS elements. We do observe a marginal degradation in performance due to estimation error. Yeah, and the approximations seem reasonably tight with imperfect CSI. Here what we do is we plot probability of outage in wet as a function of the power that these sensor nodes spend in sending out pilots on the uplink. And what we notice is that there are 3 regimes here basically. So if the sensor node spends too much energy on the pilots, it ends up spending more than, so it ends up consuming more than what it harvests. So we do see an increase in outage. Over this range of pilot power, the performance is relatively insensitive to estimation error. But then as the pilot power is reduced further, outage increases due to poor quality channel estimates. Yeah. And then, yeah, increasing the number of IRS elements help lower the outage probability. Yeah. So we do see a marginal gap between perfect and imperfect CSI. There's an example to illustrate the impact of discrete phase shift. So as we increase so this is with 1-bit quantization. So the performance with 2 phase shift levels, with 4 phase shift levels, with 8 phase shift levels. So what we notice, so we should understand that in order to induce 2 to the power j phase shift levels, j pin diodes are needed. And IRS element design becomes more challenging due to its limited size if we add more pin diodes. So the conclusion from this is that 3-bit programmable IRS suffices to achieve a good trade-off between complexity and performance. Yeah, now let us look at an extension where let us say the source is not necessarily equipped with just a single RF chain. It has n RF chains where nRF is less than equal to m. Yeah, so nRF equals m refers to the full complexity system. Now for this scenario, what is essentially done is that the direct link channel power gains, they are arranged in descending order. And the nRF antennas with the highest channel gains are selected. Now using those antennas, the active beamformer at the source, yeah, since we have multiple antennas, one can perform beamforming at the source as well. And passive beamforming at the IRS, one can design that based on alternating optimization, where the key idea is to maximize the receive power alternately over one variable, keeping the other fixed until convergence. So we'll look at one more aspect, which is related to the power transfer efficiency. So this is essentially referred to as the ratio of the average power harvested by the user to the total average power consumed at the source. And we consider the following model for power.
Salil, can I interrupt for a minute?
Yes.
In the previous slide, I'm just trying to understand the intuition behind that rule where you select the antennas with the highest channel power gains. So are you assuming that the user has only one antenna always, or?
Yes, sir. I mean, user is equipped with single antenna in the model.
Oh, I see.
Yeah.
Then
and sir, the feeling, I mean, this rule seems to work because perhaps the channel along the cascaded path is not as strong as the channel along the direct path. Because the path loss here is of the order of, let us say, 10 power minus 6 times 10 power minus 6. But here, the path loss is just 10 power minus 6.
Okay, thanks. And just one more question, if I can. In the previous simulation results that you showed, what correlation model did you assume for the channel?
Okay, so all these channel, so all these results are for spatially uncorrelated channels. We have a set of results with spatial correlation where we have taken the Nazafi-Schober model. I'll point to that paper towards the end.
Thanks. Yeah.
But so far all these results are for spatial uncorrelated channels. Yeah. All right, so power transfer efficiency, the power consumption at the source is modeled this way, where PC equals PTX, where PTX refers to and is essentially the ratio of the source transmit power to the power amplifier efficiency. P fix refers to the fixed power which is required to run the source. NRF, number of RF chains. PS is the circuit power consumed in every RF chain at the source, and PLP refers to the power consumed in computing the active beamformer at the source, and it essentially depends on the number of RF chains, number of users that you're serving, bandwidth, number of time frequency samples in a coherence interval, and KS refers to the source computational efficiency measured in flops per watt. PE refers to the power that is spent in configuring phase at each IRS element. Yeah, so now given this power consumption model, this example essentially illustrates the impact of number of RF chains on the power transfer efficiency. What we note, so we've considered a setup where the source is equipped with 32 antenna elements, and then we vary the number of RF chains. So what we notice is that as the number of RF chains increase, initially we do observe an increase in the power harvested by the sensor node due to energy beamforming. But then it then reaches a maxima, and then it starts decreasing because the power consumption at the source dominates over the power harvested by the sensor nodes. All right, and the other thing that we observe is that the power transfer efficiency does improve as you increase the number of IRS elements from 50 to 75 to 100. There's an interesting result where what we show is, so we again plot probability of outage and wet as a function of the source transmit power for two different number of IRS elements, 50 and 150. Now we have four set of curves here, different configurations. So 1,4 refers to a single antenna selection system. 2,4, 2 RF chains, 4 antennas at the source. 3 RF chains, 4 antennas, and this is a full complexity system. Now, what we observe is that for a given transmit power, yeah, so if we draw a vertical line, so for a given transmit power, C equals 1,4 with N 150, it outperforms C equals 4,4 with N 50. Yeah, so essentially one can trade off active RF chains at the source with passive elements at the IRS in order to boost performance, or in order to obtain improved performance. Now, talking about extension to multi-user scenario. In the multi-user scenario, what we do is, so we will focus on single RF chain at the source, M antennas. Yeah, now we have K users in the setup. Now we were looking for a solution where we can directly extend our analysis that we have done for the single user case to a multi-user scenario. So the model here is as follows. We consider that every user is served based on round robin scheduling. Yeah, so essentially the coherence interval tau is divided into u slots or k slots here, since there are k users. So, and every user is served in tau by k duration, over tau by k duration. Now, in that case, yeah, and in a multi-user scenario, how do we define outage probability? It is essentially 1 minus the probability that every user harvests the certain bare minimum that it needs. Yeah. So now, one thing to note here is that these events are not mutually independent. This is because although the users are being served in disjoint slots, so that does simplify. So in every slot, basically, the source would select antenna that sees the strongest channel along the direct path to that user, and the phases can be configured accordingly. But then these events are not mutually independent because the source may end up selecting the same antenna for different users. And in that case, the source to IRS link will be common for different users. Yeah, so that makes these events, that introduces some kind of correlation among these events. So to tackle that, what we did was we upper bound this using Wolf-Freshe inequality. Yeah, and so which is outlined here. So probability of intersection of R events is lower bounded by the sum of probabilities of those events minus R minus 1. So max of these two. And this is what we obtain with perfect and estimated CSI. One can do a similar analysis with estimated CSI as well. And the key conclusion here is one can support a larger number of users. One can support wireless energy transfer to a larger number of users just by adding few extra IRS elements. And one more thing that we note is that the upper bound that we obtain based on Wolf-Freshe inequality is reasonably tight. Yeah, so just to conclude, what we have looked at is a model where the source is equipped with fewer RF chains than the number of antennas, and it performs wireless energy transfer. We propose a joint antenna selection and passive beamforming rule. We look at outage performance with both perfect and estimated CSI. What we find is that the proposed ES rule is near optimal with while requiring fewer pilot transmissions. It helps us obtain significant savings in radiated power by increasing number of IRS elements or antennas. And one can essentially trade off active RF chains at the source with passive elements at the IRS while obtaining improved performance, both in terms of outage probability and power transfer efficiency. I thought I will overrun the time, so I did not include the results with spatial correlation. But then the model for spatial correlation is pulled from this paper, which is physics-based modeling and scalable optimization of large intelligent reflecting surfaces. So all they do is they consider scatterers along. So this is not the sync model used in most papers written by Emil and group. This is so what they do is they essentially they consider a certain number of scatterers along each of these links from source to IRS, from IRS to user, and source to the user, and they construct low rank channels. Now, depending on, so what we observe in our results is that as the number of, as expected, we observe that as the number of scatterers increase, the performance improves. What we also observe is that so the spacing is important, spacing among these IRS elements. So if the spacing among these IRS elements, it is reduced from lambda by 2 to lambda by 80, for example, then the spatial correlation increases. Then it makes sense to group these IRS elements. Yeah, so let us say the 4 adjacent IRS elements can be grouped together, and all the IRS elements within the group, they can be configured with identical phases to obtain improved performance. So all right, yeah. So furthermore, in this model, they also consider that the amplitude change induced by every IRS element is not necessarily 1. It does depend on the angle of arrival and the angle of departure. Yeah. So with that, I'll stop. If there are any questions, I'll be happy to answer. Yeah, so I'm audible, right? Yes.
Yes. So thank you, Professor Salil Kashyap, for an informative talk. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is a mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box. The link to the recorded video will also be posted on the web page. Thank you and have a great evening.
Thank you. Thanks a lot.